They're saying that we have a frequency of 693 kilohertz, which it uses for broadcasting. And they're asking us how is it possible to receive these broadcasts in a house on the other side of a hill from a radio station, and it should include an appropriate calculation. So basically, the basic theory behind this is in the belonging to the chapter of communications, which is in Cambridge A2 syllabus. Okay, I'll try updating my notes for that Excel, including this part in there. So basically what happens over here is that you've got a radio station over here, okay, and it is producing some signals. These signals which are produced, they are sent to a satellite up there. The satellite receives these signals, amplifies them, boosts them, and then sends them to the consumer over here. Okay, and these signals, when they were sent from the base station from Earth, they experienced great attenuation on their way to the satellite. Attenuation means they suffered lots of power losses during their way to the satellite, because as they were going up, the radio waves or the radio waves, when they were going up, they had to pass through several resistances. For example, the clouds, and the distance that they traveled, and etc., due to which they had used up a lot of their energy when they reached the satellite over here. And then the satellite, this signal that goes to the satellite is called the uplink signal. And as the signal is received by the satellite up here, the satellite boosts the signal. Okay, it boosts it up and sends a slightly different frequency signal back down. Okay, this frequency now, the boosted signal that is sent, it has a second frequency, and this frequency is slightly different from the one which was sent up there. The reason for that is because this is a boosted signal, and the signal which was coming up, it is a weak signal because of the attenuation that it has suffered. So this signal might swamp the other signal. The term used here is swamp. It might interfere with the other signal which is coming up there, because of its high in energy. The signal is the boosted signal. The signal which is going to be received, the uplink signal, is a weak signal, and the downlink is the boosted signal. So the downlink signal uh, might completely interfere with the uplink signal, and then this boosted signal is sent down to the receiver, where it is
Where is the satellite booster kept?
sorry.
Is that like satellite in the space, or?
Yes, its satellite is in the space, of course.
Okay, but won't it take a lot of?
No, it won't take a lot of time. The reason for that is because the speed of radio waves is very high. It's the same as the speed of light, 3 raised to the power of 8 meters per second. So it's relatively very fast. Okay.
Okay.
Yeah, the speed of light is extremely fast, so that's why it doesn't take longer for it to reach the other side.
Yeah.
Okay, so the value for lambda turns out to be how much? So what is the velocity of radio waves? It's the same as
3
speed of light,
to 10.
10
Oh,
raised
yeah.
to the power of 8, and the frequency is 693 kilohertz. Can you give me the answer to this? 3 raised to the power of 8 divided by 693 times 10 raised to the power of 3. This turns out to be 433 meters, right? 433
Yeah.
meters is the wavelength of this radio wave. Now this wavelength of the radio wave, if is comparable to the size, meaning 493 is quite a relatively large size, right? It is like a big size, a measurable size, a significant size, 433 meters. So now this size is large enough, it is comparable to the mountain size, the size of the mountain. So what would happen over here is that as these waves, as they reach the mountain peak or this mountain, the mountain is an obstacle, right? It's an obstacle in the way. So over here, this wave will get diffracted, because diffraction is possible only if you get an obstacle which is comparable in size to the wavelength of that particular wave. And these two are comparable. Okay, so over here, as soon as the wave reaches, it gets diffracted. Diffraction means it gets spreaded. Okay, it changes its shape into a geometrical shadow, and from here it reaches this consumer. Okay,
Right.
so that's the theory they want you in your marking scheme, and that's also correct. If you are not considering the satellite communication, then yeah, this is the second way of explaining it. So I guess you should stick to this method and not go to the satellite communication. Okay, so
Okay.
let me write down all the points which you need to include in your answer. I'll write it down here. Okay, so basically, first of all, you need to show this calculation that v is equals to f lambda, and then lambda turns out to be 433 meters. Okay, meaning after all this, all these steps, you show these steps, and then you get this answer. You get your first mark. Then you say that the wavelength is comparable to the mountain size. Wavelength is comparable to the mountain. And then you say that at mountain diffraction occurs. Diffraction of the wavelength occurs. Of radio waves occur. And then you say that as they are diffracted, they reach the consumer. You also need to mention that the mountain is your obstacle, okay, compared to the mountain, which is your obstacle.
Okay.
Yeah, and let's look at the marking scheme once again. Mention of diffraction. Wavelength is comparable to the size of the hill. V is equals to f lambda. Lambda turns out to be 433 meters. Okay. Now do you get it?
Yeah.
Okay, now part B says the radiation flux of the radio waves arriving at the particular house is this much. Okay, watt per meter squared. Okay, let me explain what this actually the unit represents. Watt per meter squared. Watt is a unit for power. Power means joules per second, right? Power means joules per second, energy per unit time. Is that so? Is watt equal to joules per second?
Yeah.
Because power is energy upon time, right?
Yeah.
Okay, so instead of watt, I've written joules per second, and the meter square stays at its place. Energy per unit time per unit area. This is actually the formula for calculation of intensity. If you would have seen the wave lectures, I've given this formula for calculation of intensity. The energy per unit time per unit area. Okay, now they've given us the intensity of the wave which is reaching the house. Calculate the energy arriving at a person's head from these radio waves in 1 hour. Area of the head is given to you. Okay, so they've given you the area, they've given you the time. All they want you to do is just calculate the energy. Simple. What's the formula for intensity? Intensity is equal to energy upon time multiplied by area. Okay, this is the formula for intensity as we just figured it out from here. They want us to calculate the energy. Okay, energy is needed. The area of the head is given to us, is 0.025 meters squared. The time is given to us, it's 1 hour. 1 hour means 3600 seconds. Okay, you have to convert it to seconds because you have to do the calculations in SI units. And then you have the intensity as well, which is 8.3 raised to the power of minus 9. 8.3 raised to the power of minus 9 watts per meter squared. Now you have everything. You just use this formula, you plug in and you get your answer. Okay, so energy turns out to be this intensity multiplied by time multiplied by area. Intensity, okay, you just please calculate the answer. Intensity times time times area, which is 8.3 times 10 raised to the power of minus 9 times 3600. times 0.025, which is 7.47 raised to the power of minus 7 joules. Okay, this is the energy in joules. Yep, that's the answer. 7.47 or 7.5, same thing. Okay, they've rounded off to two significant figures. We've left it in three significant figures. Get it?
Yeah.
Please take a screenshot and then I'll move on. This constant H, the Planck's constant, was named after the scientist Max Planck. It has a fixed value, 6.63 raised to the power of minus 34 joules second. Okay. Now, so you have to give the reference to photons as well over here. This is correct, but this reference needs to be given.
Right.
So let me give you the mark distribution over here. This is the very first mark. Then you have to say that energy of a photon, okay, you have to just bring it in one statement. Energy of a photon is proportional to the frequency of the electromagnetic radiation. And you can also write this formula down because it also represents this relationship. And then you could say that photons with greater energy or greater frequency causes more penetration and therefore more ionization of the body cells. And the radiations that cause ionization are the ones that cause more damage to the body. And you may give reference to cancer as well. Okay, it won't be wrong because it does actually cause cancer. Okay, ionization actually means causing cancer. Okay, because ionization is actually the cause of cancer. That it, should I write it down in a paragraph form, or is it okay?
Yeah.
Variety of colors is often seen when white light is reflected from a thin layer of oil on a puddle of water. This is actually called the interference of thin films. Okay, interference in thin films. Although not a part of the syllabus, but this is actually a suggest type question. I know this from my uh, further knowledge, so that's why I did this somewhere else. Now, light reflecting from the top of this layer of the oil undergoes a phase change of 180 degrees. This results in the phase difference of 180 degrees. Okay, phase shift of 180 degrees actually mean that the light ray was coming straight, and as soon as it
And
gets
reflected
reflected,
off.
its shape actually becomes reflection of its original self. Okay, something like this. So now it has shifted by 180 degrees. This is what the 180 degree shift actually means. Okay, and now these two waves are actually out of phase and they might form stationary wave as well. Then it says explain what is meant by a phase difference of 180 degrees. Phase difference of 180 degrees actually mean that the two waves are completely out of phase. Waves are out of phase, completely out of phase. Okay, and they'll interfere destructively. Destructively means that the resultant wave that is going to be made is going to have an amplitude or a displacement that is going to be a difference of the two waves displacement. Okay, so they'll interfere destructively, and they'll have they are completely out of phase. They'll interfere destructively. Resultant wave, if the two waves are actually a reflection of one another, then that actually means that both the waves might cancel each other out. Okay, so let's verify it from the marking scheme as well, the points that we need. Waves are in antiphase or waves are out of phase, and then destructive interference. We got both the points. Okay, is this clear? Okay, of a thickness d on the surface of water, a ray of white light is incident on the layer of oil and reflects from the top and bottom surfaces of the oil. Light reflected from the bottom surface does not undergo a phase change. Okay, they are saying that light reflected from the bottom surface does not undergo a phase change. And the light that reaches over here does not undergo a phase change. Okay, let's see why are they saying that. Calculate the velocity of light in oil. If the refractive index of oil is given to you, it's 1.5. Okay, what's the formula for calculation of refractive index? Refractive index, there was one formula which we did in O levels, is equal to the speed of light in vacuum divided by speed of light in the medium, if you remember it. Speed of light in vacuum upon the speed of light in the medium. This is one formula for refractive index which we did in O levels. Refractive index is 1.5. The speed of light in medium is asked, so let's assume it's x, and in vacuum it's the same, 3 raised to the power of 8. This turns out to be 3 raised to the power of 8 upon 1.5. 1.5 times 2, and then this turns out to be 2 raised to the power of 8. But give your answers to two significant figures, okay? Meters per second. This should be the answer. Let's verify it. Yep, that's the answer. You get it? You get the formula? Yes, they are called photons. These are packets of energy. These photons, when they are incident upon a metal surface, upon a clean metal surface, what they cause is these photons, since they are also particles on the metal surface, if there are certain electrons, let's say there are certain electrons present on the metal surface, these photons come, these photons are absorbed by the electrons, they cause the electrons to be emitted with a certain kinetic energy. Actually, they are emitted, and the extra energy that we provide, it goes and converts into the kinetic energy of the electrons. This
There's an emission of electron from metal.
Yes, emission of electrons from the metal surface, not from the metal, not
Yeah.
from anywhere
Okay.
inside, only from the surface, okay? That emission of electrons from the surface of the clean metal surface is known as the photoelectric effect, okay?
Yeah.
Let's see the definition which is given over here. It says that photons are absorbed, energy is transferred to the electrons, electrons are released. When the incident photon has energy greater than the work function. Well, now let me explain you what the work function is. Work function is the threshold or the minimum energy needed to cause the photoelectric effect. The minimum energy that photons must possess. The minimum energy possessed by the photons.
Oh, sister, wait, can you give me 3 minutes? I'll be back.
Okay. That external light source falls on this metal plate, then what do you think will happen? Electrons will be emitted, right?
Yeah.
Those electrons which are emitted, they'll go straight. Due to the photoelectric effect, they'll have some energy, kinetic energy basically, okay? They'll be emitted and they'll go in, and as they reach this plate over here, current will start flowing through the circuit, and that current will be detected over here. Clear?
Yeah.
Okay, now over here, that kinetic energy with which the electrons flow is given to you, and the frequency is given to you, and we need to use this graph to determine the Planck's constant. Okay, so basically the formula for the energy of the photons is pretty simple. Energy of the photons is equal, basically the total energy of the photons is equal to the work function energy plus the kinetic energy of the electrons. Okay, what do I mean by this? Let me explain it over here. So for instance, if you have some electrons, over here, and the electrons are present inside the metal surface. Electrons are present inside the metal surface, then there would be some energy needed to move these electrons to the metal surface first, right? Some energy will
Yeah.
be needed to move them to the metal surface, and after they reach the metal surface, they'll be emitted out. This emission is the photoelectric effect, and the energy which is needed for the electrons to move up is your work function energy. Okay, after the photon's energy has been consumed in moving the electron to the surface, the rest of the photon's energy gets converted to the kinetic energy of the electron. So the total energy that the photon brings, it converts into two forms of energies. First one is the work function energy, and the second one is the kinetic energy of the electrons. Now, in this graph, after this frequency, your electrons are emitted. This is your threshold frequency, the 4. See, before the 4 raised to the power of 14 hertz, before this frequency, no emission was there. But immediately
Right.
after this frequency, you've got emission at a constant rate. This emission is this frequency is called the threshold frequency, okay? The minimum threshold that you require to cause the photoelectric effect, the threshold frequency. This threshold frequency can be calculated using the formula HF naught, meaning the work function is equals to HF naught. The work function, the value for the work function is not given in the graph, so we cannot use this formula over here. Instead, what we can actually do is we can use the graph of this we can use the gradient of this graph. Okay, why the gradient? Well, that's because energy is equals to HF, right? And H is equals to energy divided by the frequency. Energy divided by frequency is your Planck's constant. Is that so?
Yeah.
If energy divided by frequency is your Planck's constant, and Planck's constant is actually a constant, it will stay constant. So if we calculate the gradient of this graph, we will actually get the value for the Planck's constant. Okay?
Okay.
So now to calculate the gradient, we'll take the values over here. It's 4 raised to the power of 14 and 0. And somewhere on this graph, okay, let me take a value over here. This seems like this is 6 and this is 7. So this is 6.4. 6.4 raised to the power of 14. And on the y-axis, it's 1.5 raised to the power of minus 19 joules. Okay, so we've got these 2 points. Now use them to calculate the Planck's constant value. So 4 times 10 raised to the power of 14 and 0. And please give me the answer to the gradient. 6.4 raised to the power of 14 and raised to the power of 14.
What do I calculate?
Gradient slope 1.5 raised to the power of minus 19. The slope turns out to be y2 minus y1 over x2 minus x1. So 1.5 raised to the power of minus 19 minus 0 divided by 6.4 raised to the power of, this is 14 minus 4 raised to the power of 14. And the answer to this should turn out to be
6.25 into 10 to the power.
minus 34. Yes, that's the answer. 6.25 raised to the power of minus 34 joules second is your answer, and that is actually the value of the Planck's constant. The Planck's constant value is 6.3 raised to the power of minus 34. Actually, it's not 6.3, it's actually just 6, meaning we just leave out the 2.5. That's 0.25. Okay, that's correct. So what does the marking scheme say? Calculation for the gradient of using at least half the gradient, half the graph, sorry. Okay, whenever you need to calculate the gradient, try using as much as the space of the line as possible, okay? At least half the graph should be covered while you are calculating the gradient, and that's actually a rule to get an accurate answer, okay? You could have used this point or point somewhere over here, but not a point too close. Otherwise, that will give you a wrong answer or a non-accurate answer. Clear?
Yeah.
So we actually didn't need this formula for this calculation anyway. But this is also a formula that is used. Okay, I'll send you the video, then everything would be clear, inshallah. And moving on to part 2, describe the significance of the frequency of light having a value of 4 raised to the power of 14 hertz. In this experiment, they are asking us the significance of this frequency over here. What is this frequency? What is the name of this frequency, which I just told you? It's
Which one?
this one,
The threshold frequency.
Threshold frequency, correct. So the 4 raised to the power of 14, this is the threshold frequency. This is the threshold frequency. And what is the threshold frequency? The definition of a threshold frequency is the minimum frequency that must be possessed by the photon in order to cause the photoelectric effect. Okay, this is the threshold frequency, which is actually the minimum frequency that the photons must possess. Minimum frequency that the photons must possess to cause the photoelectric emission or to cause the photoelectric effect. Clear? So let's see what did they write. Threshold frequency, lowest minimum frequency that will cause photoelectric effect. Okay. Then calculate the work function of this metal in electron volts. Okay, they want us to calculate the work function. What's the formula for the work function? Work function is equal to HF naught. Okay, this is the formula for work function calculation. Work function, as I told you, it is the energy. The formula for energy of photon is HF, right? If this frequency becomes the threshold frequency, F naught is actually the threshold frequency, okay, which they've given us in the graph, then this energy becomes the work function, okay? Should I repeat what I just said?
Yeah.
Work function, what is work function? This is the minimum energy that a photon must possess to cause photoelectric effect, right? Minimum energy required by the photon to cause photoelectric effect. By photon, this definition is asked, okay, to cause photoelectric effect. Now, if this is energy and this is the energy of the photon, what's the formula for calculation of energy of a photon? It is E is equals to HF, right?
Yeah.
Now, since E is actually the minimum energy which is needed to cause the photoelectric effect, the value for the frequency is also going to be the minimum frequency required to cause the photoelectric effect.
Right.
Okay, makes sense. So that's why we are going to use HF naught. The value for H is fixed. It's 6 raised to the power of minus 34. The value for frequency is given to you is 4 raised to the power of 14, I think. Yeah, 4 raised to the power of 14 hertz. And when you multiply them, you get an answer. 6 times 4 is 24 raised to the power of minus 20. And this will give you 2.4 raised to the power of minus 21 joules. Now, this is the answer for work function in terms of joules. But what did they ask us in? They asked us in electron volts. So what's the conversion factor from joules to electron volts? 1 electron volt equals 1.6 raised to the power of minus 19 joules. So if we have 2.4 raised to the power of minus 21 joules, how many electron volts do we require? So we are going to just divide this number by 1.6 raised to the power of minus 19, and you'll have your answer, which is 0.015, meaning 1.5 raised to the power of minus 2 electron volts should be your answer. What does the marking scheme say? They've given us a different answer where there's some sort of calculation error. HF naught equals to phi, and the F naught value which they used was, why is it? Okay, there must be some calculation error over here. Let me recheck the calculation. 6 raised to the power of minus 34 and multiplied by The value for the frequency is 4 times 14. Okay. So multiplied by 4 times 10 raised to the power of 14. It's 2.4 raised to the power of minus. Oh, okay, sorry about this. This is 2.4 raised to the power of minus 19 joules, not minus 20. Not minus 21, it's minus 19 joules. Okay, this is actually the calculation error that we have. This is minus 19. Okay, so the 19 would cancel out, and so the answer that you'll get is 1.6 raised to the power of minus 19 is 1.5. We get 1.5. They have 1.7. The reason, I'll tell you the reason for that. Okay, they have given 1.5 as the answer, so that's the answer. Okay.
Okay.
Yeah. So let's move on to the next one then. Okay, so this is from DC circuits, a very good topic, quite an easy topic. Just a second. A geophysicist may use resistivity to determine the different materials within the ground. Two electrodes and a 12-volt battery are connected to 2 points of 0.8 meter apart in the ground. The length is given to you, the voltage is given to you. Arrangement is used to measure the current in the ground between the electrodes. Sorry. Okay, so between the electrodes, these are the two electrodes that you have, and current in the ground is needed to be calculated. The effective cross-sectional area of the ground is given to you, and the current between turns out to be this much. Calculate the resistivity between the electrodes. Any formula which relates all of these quantities? What's the formula for resistance using Ohm's law? V is equals to IR, right?
Yeah.
V is equals to IR. We can use it to calculate the resistance because voltage and current are given to us. So voltage is 12 upon current is 8.5 raised to the power of minus 3. The resistance turns out to be something which is 12 upon 8.5 raised to the power of minus 3.
1411.8.
1411.76 ohms. Now you have the resistance. You also know the other formula for resistance. Resistance is equal to rho L over A, where rho represents the resistivity, right? They want us to calculate the resistivity. So you just make rho the subject. So rho equals RA upon L. The formula, the value for R is 1411.76. You multiply it with the cross-sectional area, which is 0.25, and divide that by the length, which is 0.8, and the answer that turns out to be how much? Multiply by 0.25 divided by 0.8 is 441, meaning a 440. Two significant figures is 440. Let's see. Yeah, 441 is the answer, or 440 is the answer. Same thing. Next one says, the graph shows how the resistivity varies with the depth below the ground level at a particular location. The geophysicist has also made a sketch of the different layers of the materials beneath the ground at this location. This is the wet subsoil, this is the topsoil, this is the ground level, 5 meters, okay, and this is the bedrock. You've gotten the resistivity, and this is the depth below the ground. Now at 5 meter over here, you get the bedrock. Okay, after the 5 meter, you get the bedrock actually. Beneath the 5 meter, you get the bedrock. And if you look at it carefully, the resistivity sharply rises after the 5 meter and then becomes constant at a very high value. So now let's see, explain how the sketch of the graph corresponds to the graph. Okay, so basically this is your sketch, and this is the graph, and this is the sketch. First of all, the topsoil, and this is the ground level. Now, we start out from here. Okay, we start out. As soon as we enter the topsoil, the resistivity starts falling because topsoil is having a low resistivity. Then as we go beneath and as we reach the wet subsoil, the resistivity falls even low because it's wet, right? It's wet. It is conductor. It won't have much conductance because water is a good conductor, right? So that's why resistivity is the ability to resist. Sorry, it is a property of the material. So resistivity is a property of material which is actually related to the resistance of the material. So this part will have a lesser resistance. And then as we go beyond the wet soil, as we go beneath the wet soil, in the bedrock resistivity increases sharply and then becomes constant as we go down approximately at a higher value than original. So explain how it corresponds to the sketch of the graph. So first of all, the topsoil has a fair resistivity, okay, but as we go beneath the topsoil and reach the wet soil has a lesser resistivity compared to the topsoil. This is the first point to write. Wet soil has lesser resistivity than topsoil. And if we need to explain it, so explain the reason for it. Reason, because as water is a conductor, so has a low resistance. Okay, so therefore the graph falls. Therefore, the resistivity value decreases on the graph. Decreases. But as soon as we cross the 5-meter depth and reach the bedrock, resistivity increases sharply. Since bedrock has a high resistance. Bedrock, it is a rock, right? Has high resistance. As it is a better insulator. So let's see what the marking scheme has stated. Says a value for the resistivity of a layer. Okay, we didn't state any value. Makes a comparison between the resistivity of the layers. Yeah, we did that. And between the topsoil and subsoil, the resistivity decreases slowly, indicating a varying depth or inclining the subsoil. Or at 5-meter depth, it increases suddenly, indicating the constant depth of bedrock. Okay, we didn't indicate that, but we did say that it increases rapidly after the 5-meter part. And indicating the constant depth of the bedrock. Let's see the constant depth immediately after the 5-meter, it increases rapidly. So it indicates the constant depth because anywhere over here the resistivity will be the same. So that's why it rises sharply and gets a great value. Okay, so we did say that it increases sharply, but we didn't say that that's because of the constant depth of the bedrock. And that's actually quite visible from the sketch as well, because if you look at the line of the bedrock, it's a horizontal line, right? It's not a wavy line having varying depths. It is a constant line over here, not like the subsoil over here. See, the subsoil line is wavy. This is straight. The straight line shows a constant depth inside. So yeah, it increases rapidly. We did note that point, but we didn't write the second point. So increases rapidly at 5-meter depth, showing the constant depth of the bedrock. And there's another thing that the examiner wanted, and that was identifying a value for one of these layers. See the very first one, state a value for the resistivity of a layer. So for such questions, you should state a value for the resistivity of any of these layers. So for bedrock, I think we should state a value for bedrock, it's constant. Or we could start out by stating a value anywhere over here. For example, the wet soil. The wet soil has a value somewhere over here. It's approximately 100. So resistivity of wet soil is approximately 100 ohm meters. So this statement also had 1 mark. So for graphs, try stating the points whenever you get a graph next time in the past papers, okay? Is this question making sense? Okay, so if this is entirely a series circuit, then that actually means the current has a constant value.
Yeah.
If the current is constant, then the voltage is actually proportional to the resistance.
Okay, right.
And now you also know from the other formula for resistance that rho is equal to L upon A. They told us cross-sectional area is constant and rho is constant because it's the same ground. So can I say that the resistance is proportional to the length as well?
Yep.
Now, if resistance is proportional to the length and resistance is also proportional to the voltage, I can say that the voltage is actually proportional to the length, because
Okay.
resistance is the common person in there, right? Hello?
Yeah.
Okay, so now if voltage is proportional to the length, now I'm going to use this relationship to get the value for the voltmeter, and it's going to be pretty easy. Now see, whenever you have a direct relationship, you can say that V1 upon V2 is equal to L1 upon L2, right?
Yep.
If V1 upon V2 is equal to L1 upon L2, then what is the value for V1? If you look at this part, for the entire length of 0.8 meters, the value for the voltmeter was, the voltage applied was 12 volts, right? 12 volts was applied for the entire length of 0.8 meters. Then if the length is reduced to 0.2 meters only, what would be the voltage across that point is what we need to calculate, right? So if this length is 0.2 meters, then what is the second voltage? Now to calculate the value for this is going to be 4, and V2 turns out to be 12 upon 4, which is 6 upon 2 or 3, and so voltage should be 3 volts. Get it? 3 volts. Voltage is proportional to the length.
Wait, what did you take V1 and V2 as?
The voltages, the two voltages across the two lengths. The
Okay.
V1, like you can take any of these as long as, basically if you
Not
consider,
getting
if you consider the 12 volts as V1, then this entire length is going to be your L1. If you consider V as V2, then this length is going to be your L2. Clear?
Okay.
Yeah. So, but examiner has 3 marks given to you in this question, and one of them is for stating that voltage is proportional to the resistance when current is constant. Current is constant, and then stating the other point that resistance is proportional to the length, therefore the voltage is actually proportional to the length. Okay, these parts also have marks, that resistance is proportional to the length and the voltage is proportional to the length.
Okay.
Okay, yeah, clear? That's why they've given 3 marks for this question. Should I move on?
Yep.
Give one reason why this method leads to a more accurate result than the method described in part A. This is a potential divider circuit. And in potential divider circuit, we know it from theory that potential dividers are better than any other voltmeter. The method they used in part A is over here using only one voltmeter device, and the cross-sectional area of the ground is given, the effective cross-sectional area is given, then the current is measured, and the length is given, 12 volts is given, which is applied across only one length, and over here we are on move. In part B, we are actually using two lengths. Okay, so the greater the values of length, the more accurate the answer that you get. So that's the reason actually. So what did they write? Cross-sectional area will be more constant over a small length, less variation in resistance over a shorter length, eliminates contact resistance of electrodes with the ground, combines both methods so the two values of resistivity can be calculated and compared. Um, okay, so they've given you a lot of answer options over here. So I'll explain you the first one. Over here, they've given you a shorter length and they calculated the voltmeters, just voltage across this shorter length and use it to calculate the longer, actually, sorry, they calculated the shorter length voltmeters reading and then used it to calculate the resistivity. Whereas if you compare it with the first one, for the first one, they used this entire length, this entire 0.8 meters, and then used it to calculate resistivity. So this entire length might not have a constant area. Whereas for a shorter length, the area being constant is going to be more likely. The area is going to be more likely to stay constant for a shorter length. Because of course it's ground, it's going to be uneven. But like for the shorter length, it's going to be more uniform as compared to the longer length. So therefore less chances of error. So you're going to write down that shorter length will have a more constant cross-sectional area. Giving a more accurate value for resistivity. Because both the experiments are conducted for calculation of resistivity. Is this clear? Voltage over here, because 1.5 and then 1.5 and they are in series with one another, so their voltage will combine. Now when this switch was closed, these two bulbs were lighted with normal brightness. So this actually means that these two bulbs were the only ones connected in the circuit, because when the switch was open, no current was flowing through this branch, right? No
Yeah.
current was passing through this branch, and all of it was passing through this branch over here. So if all of the current was passing through the branch, the total voltage is 3 volts. What's the voltage split in between the two bulbs? It's 1.5 and 1.5 volts, right? Both the
Yeah.
bulbs are getting what they require for the normal brightness. Both of them
C
require
will
1.5 volts. But
oh C
as
will get like 3 volts, so it will be the most bright.
it won't get 3 volts. Nope.
Why not? Because it's in like it's parallel.
It's parallel, but it's not parallel to the battery. It's parallel to A. If
Oh.
this junction was not over here, but rather it was over here, then it would have gotten 3 volts and it would have fused, because it's going to be greater than its normal
Right.
voltage. But since it's over here, it's not in parallel with the cell. Now, what you need to do is you need to consider, as soon as this switch closes, you need to consider both of them as a single unit. When you consider both of them as a single unit, that actually means you're combining their total resistance. When you combine their total resistance, what happens? Whenever two bulbs are connected in parallel to one another, their combined resistance, it becomes less than their original individual resistances. Okay, remember that in parallel the resistance always becomes lesser than the actual resistance. So now if just assuming, and they told us they are identical lamps, right? They told us they are identical lamps. Hello.
Yeah.
So identical actually means their resistances are also the same. So if we assume the resistance of A is R and the resistance of C and B are also R and R, if we calculate the total resistance of the two connected in parallel to one another, what is it going to be? The formula for calculation of the total resistance for parallel is product upon sum. The product is going to be R multiplied by R and the sum is going to be R plus R, right?
Yeah.
R multiplied by R will give you an answer of 2R or R squared?
Oh, 1.5 into 1. Wait.
No. You don't have the resistance value. Just give me in terms of R. R times R is R squared now. It's R squared, right? And R plus R is 2R. So this is your total resistance. The R and the R squared will cancel out, and the effective resistance turns out to be R upon 2. Is this clear? Now these two resistors are in parallel with one another, so their effective resistance is going to be R upon 2, and the effective resistance of the third one is R. Now if this is R upon 2 and this is R, what's the voltage drop across R upon 2 and what's the voltage drop across R? Any suggestion? You can calculate the voltage drop by using the formula V being proportional to R, because now the current that flows through this entire component is going to be the same as the one which passes through B. So this entire component and this component is actually, they are both in series with one another, right? B is in series with their combination. So voltage is actually proportional to the resistance. So now the resistance is R upon 2 for this combination and it's R for the B. Then that actually means we can use the ratio method to calculate the voltage drop across both of them, right?
Right.
So the formula is going to be V1 upon V2 equals R1 upon R2. You can use this method. So the total resistance that you have and the total voltage, V1 is, let's assume V1 to be the total voltage and V2 to be the total resistance. What's the total resistance? It's going to be R upon 2 plus R, right? The total resistance of the circuit. Is it going to be R upon 2 plus R? Hello?
Yeah. Yeah.
It's R upon 2 plus R, the total resistance, right?
Yeah.
Because these two are in parallel to one another and this is in series to that, to both of them. So now it's going to become R plus 2R, which is 3R upon 2 or 3 upon 2R. 3 upon 2R is your total resistance now. So the total voltage is 3. The total resistance is 3 upon 2R. Meaning I'm placing this in terms of this R1. And when you divide it by V2, what is V2? Okay, V2 can be any of these two. Okay, like V2 can be the voltage across B or it can be the voltage across A and C. Okay, so I think across B is going to be easier. So the resistance of B is R and the voltage across B is needs to be calculated. Resistance of B is R. The voltage across B needs to be calculated. The R and R will cancel out. So this becomes 3 upon voltage across B is equal to 3 upon 2. 3 and 3 will also cancel out and voltage across B will become 2 volts. Clear?
Yeah.
Now, if this is the voltage across B, what is the voltage across A? It's going to be 3 minus 2, which is 1 volt. What is the voltage across C? It's also going to be 1 volt. You understand why it's 1 volt and 1 volt? Because the total voltage is 3 and 2 volts have been dropped over here. The remainder is going to be 1 volt. That 1 volt is going to be the same as the voltage drop across C because both of them are in parallel and in parallel the voltage is the same for both of them. Clear?
Yep.
So now the voltage drop across A is 1 volt, voltage drop across C is also 1 volt, but voltage drop across B is 2 volts. Now, how do you compare the brightness of these three bulbs? Which one is going to be the brightest? Hello?
Yes.
Which of these is going to be the brightest and what will happen to the brightness now?
Yep.
Yeah, R plus R upon 2. That's why we didn't use 1 upon R1 plus 1 upon R2. Because these two are not in parallel, but rather both of them are in series. This entire combination and this part B. They are in series with one another. So we could add them up directly. And the answer to this turned out to be 3 upon 2R. Okay,
Okay.
the total resistance. So you have the total resistance and the total voltage. Now, if the resistance of a bulb is given to you, can you calculate the voltage across that bulb using ratio method? If 3 volts is the total voltage, if the resistance is 3 upon 2R, then what's going to be the voltage if the resistance is R? Use the ratio method. Clear?
Yeah.
The answer to this turned out to be 2 volts. Okay.
Okay.
Now this 2 volts have been dropped across the bulb B. So the remainder is going to be dropped across this combination, meaning this R upon 2 volts. And within this bulb, we have 2 more bulbs, right? And both of them are in parallel. So they'll also have the same voltage, which is dropped across their total. Okay. 1 volt and 1 volt because they are in parallel to one another. Clear?
Yeah.
Now these are 1 volt and 1 volt, so both of them will have the same brightness because their potential differences are the same. And this one, which has the double the potential difference, will have double the brightness. But now when you're giving the answer for brightness, the brightness is always and always given in terms of power, okay? The more the power, the
Okay.
greater will be the brightness. So the formula which we use in terms of voltage, the formula for power is V squared upon R. Now, the greater the voltage, the greater the power. That's what we applied over here.
Okay.
For part B, the voltage is greater, so the power across B is going to be the greatest, so the greatest brightness, whereas across A and C, equal voltages are there, so the power across them is going to be equal, and therefore equal brightness.
All right.
Now, to get all the 6 marks, you need to include all of these 6 points in your answer, and 1, 2, 3, 4, 5, 6. This marking scheme is pretty strict. They've only given you 6 points, so you must make sure that you write each and every point in your answer. First, you give this formula, V squared upon R. Then you say that the resistance of the parallel combination decreases. Why does it decrease? Because when you add them in parallel, their initial resistance was R and R, right? But their total turned out to be R upon 2, which is actually half of their resistance. So that's why in parallel, the total resistance of the parallel combination decreases. Okay, this is what they mean by the second point. Get it?
Okay.
So you have to mention this point as well. Then they say that the potential difference across B increases, or potential difference across A or C decreases, and that's also what we figured out over here. The potential difference across B जो है, it turned out to be 2 volts, and potential difference across A and C turned out to be 1 volt and 1 volt, which originally across A was 1.5 and across B was also 1.5, but now it's
Oh,
greater than 1.5 and this is less than 1.5. Okay, so this is also a
right.
point you need to mention. Once that's done, then they say that the potential difference across A is equal to potential difference across C. And that's also what we mentioned over here. See, 1 volt and 1 volt. We calculated this and we said that, yeah, their potential difference are actually equal. Clear? Across A and across
Yeah.
C. And then finally, so A and C have the same brightness as each other. Okay, because their potential differences are the same. Their power across them is going to be the same. Clear?
Yeah.
We need a graph of current against potential difference, current against voltage for a filament lamp. Filament lamp, remember the characteristic of filament lamp is that as the temperature increases, the resistance would increase and then the current would decrease, right? This is also a question that came in the Cambridge paper, exactly the same question, okay? While we were doing the past papers the other day, we did this question as well. Now, what would happen when the voltage would increase? As the voltage would increase across a filament lamp, will its temperature also start rising because of the heat that it generates? Across a filament lamp, if we increase the voltage, its temperature will also start rising, right? Because of the light that it would generate. it would emit, it would also have heat. The heat would cause the temperature to rise. Is that so? And now as the temperature rises, the resistance of a filament lamp rises. Okay, this is the characteristic of filament, of the
Okay, yeah,
tungsten
right.
filament. And then as the resistance increases, the current decreases. So this graph initially is going to be a straight line, but then it would become curve, it will start curving towards the voltage axis. But it won't become completely flat, okay? It won't become completely flat, but rather it will start curving. Then this was for the positive axis. What about the negative side? The negative side, as the voltage increases, the current would increase. As the voltage increases, current increases in the negative direction. But then the graph again would start becoming parallel to the voltage axis. Okay, so this is how the graph would look like. Why become parallel to the voltage axis? Because the current would then not increase as fast as the voltage because of the increase in resistance. The increase in current would become slower then. So that's why it would start curving towards the voltage axis. Let me make it properly. So this is going to be actually a curve which will go in both the directions. Okay, so somewhat like this and a curve like this. Clear?
Yeah.
This is what the marking scheme said. Exactly the same question came in the Cambridge paper. Then the next part says explain the shape of this graph in terms of electron movement through the lattice. Okay, so what do you think? Why is the shape of the graph like this? So basically, in this graph, if you look at the gradient of this graph, the gradient of this graph represents the resistance, right? The gradient represents the resistance. Sorry, not the resistance. It represents the in reciprocal of the resistance. Resistance is representing 1 upon the gradient. Why? Because according to Ohm's law, the formula is V is equal to IR. R is equal to V upon I. But over here, the gradient of this graph is going to be I upon V, which is the inverse of the resistance, right? It's the reciprocal of resistance. See, this is I upon V, that's V upon I. The reciprocal, is that clear?
Yeah.
So now, as we go at a greater voltage, the gradient of the curve starts decreasing, right? It
Mhm.
starts decreasing. The gradient decreases means the resistance is actually increasing because they have a reciprocal relationship over here.
Yeah.
So if the resistance is increasing, why is the resistance increasing? That's because of the temperature, the increase in temperature,
Increases.
and the temperature increases, it causes,
Current decreases.
yes, the current decreases, but this increase in temperature, why does it cause an increase in resistance? That is due to the lattice vibrations. Okay, the atoms which are present in the lattice, they vibrate, right? And as they
Okay.
vibrate, they provide resistance, they provide hindrance for the flowing electrons. So therefore, the current that flows, it starts falling. Therefore, the current decreases. Okay, let's write down the answer over here. Explain the shape of the graph in terms of electron movement through the lattice. So as voltage rises, the temperature rises. Temperature rises, and therefore the resistance also rises. Also rises. Why does the resistance rise? Because of the molecular vibrations, because of the increase in lattice vibrations. Increase in lattice vibrations that hinder the flow of electrons, vibrations that hinder the electron movement, that hinder the flow of electrons, and hence causes a decrease in current, the flow of electrons, and hence cause a decrease in current. The reciprocal of the gradient of the graph represents the resistance. Resistance. Therefore, as resistance rises, the gradient of the graph decreases. Gradient falls. Okay, this is this explanation. I hope that's the answer. Temperature increases with the potential difference. Increase in temperature, increase in lattice vibrations, greater rate of collisions between electrons and the lattice atoms. We didn't write this point. Okay, the rate of increase of current with the potential difference decreases. Also, this point needs to be written. These 2 points need to be written in the answer. That of course the lattice vibrations will rise, but they will cause collisions. Okay, they will collide with the electrons that flow. So this is one point. Please add this to your answer. The greater rate of collisions between electrons and the lattice of the
Okay.
atoms, which causes the increase in resistance. Then the last point says that the rate of increase of current with potential difference decreases. We wrote this point actually. We wrote this in terms of the gradient, that as the resistance rises, the gradient actually falls. So, but still at this point to be on the safe side. The rate of the increase of current with the potential difference decreases means that the gradient actually decreases. This is what they actually mean by saying that the rate of increase of the current with the potential difference decreases actually means the this gradient decreases. Okay. Let me know when you are done copying this part.